Alright, so having discussed orientation of a surface, we want to move into discussing Stokes' theorem, which is the major result from this section 7.3 from the textbook. And so here, just to review the language, so it's very similar to Green's theorem, and we'll discuss that in a later video, but we want our surface to be bounded, piecewise smooth, and oriented. Okay, we discussed what oriented means in the last video. Suppose that the boundary consists of finally many pieces that are continuous, smooth, simple, closed curves, da da da. Okay, and so then we say that the double integral over the surface of the gradient across f dot ds is equal to f dot ds, little s. Okay, so again, and I forgot one thing here. I forgot to put that this is over the boundary, or d, they call it ds. Okay, so in essence, this right here, isn't this your vector surface integral? I think so. And then this is just a line integral over the boundary. So that's interesting. Kind of, at least the form looks similar. Okay, anyway, we'll talk about that later. So let's do a quick example. Alright, so we have the upper hemisphere of the unit sphere oriented outward. Okay, let ds be the consistently oriented boundary. F is such. Use Stokes' theorem to compute that, and then find it directly. Okay, well, you could draw a nice pretty picture. Okay, I'm not going to. But instead, we're going to use Stokes' theorem. So Stokes' theorem says that this is equal to double integral over the surface of the curl dotted with this, or our vector surface integral. Okay, and so here, if we end up looking at this, if we look at gradient cross f, okay, or cross f, we end up with 0, 0, 0. Oh boy, so guess what the integral is going to be? Probably 0. Okay, so that makes our lives a whole lot easier. Okay, again, we should probably go through and verify just to make sure that we didn't violate any rules. If we're thinking about the upper hemisphere, is it bounded? Yep. Piecewise smooth? Yep. Oriented surface? Yep. It tells us the orientation. And the boundary consists of finally many? Yep, 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 yep. We're good. Okay. So in your homework, on a test, make sure to go through and verify all those. Like, just write them out, check, write them out, check. Okay. Just to communicate that you've gone through that work. Okay, if we want to find this directly, then we have a little bit more work to do. Okay, so we would have to would have to create a parameterization. So we can use our standard one. X of t is equal to, and this is for the boundary, which is the unit circle, right? So unit circle. Let's write that down. And so we have cosine t, sine t, and 0. Okay, because we're right on the xy plane. Okay, and then certainly t is within 0 to 2 pi. Okay, and then so we have to find x prime. So we get negative sine t, cosine t, and 0. Okay, same bounds. So then when I look at the line integral over the boundary, or no, we call it ds, okay. F dot ds, okay, this is going to be integral from 0 to 2 pi, and then I have to do the composition here. So we would have cosine t, sine t, 0, dotted with the derivative, minus sine t, cosine t, 0, and dt. I almost got that in. Anyway, this ends up being 0 to 2 pi of 0. So, yay, we get just 0. Okay, so our results are consistent. All right, so just a quick example of how Stokes' theorem can be used, and showing that you get both the same thing whether you do the line integral correctly over the boundary, or if you use the normal vector. All right, we'll do some more videos more examples in the next video.